Hi, welcome to the last of the muscle mini lectures. And this is a short one towards the end of your second muscle PowerPoint, and it's about muscle mechanics. So here we talk about isotonic and isometric contractions. But first of all, let's think of load. So load is the force that opposes muscle tension. So these guys here have a load, and this is the muscle tension here. So in an isotonic contraction, the muscle tension is greater than the load. So her tension is greater, she's able to hold it up here and got this load going. So that's an isotonic contraction. An isometric contraction then is where the muscle tension that's created here in the arm is less than the load. So you cannot lift this particular load. It doesn't mean that the muscle isn't trying to contract. It is, it's contracting, but it's not overcoming the load. So iso means same, metric, same length. So the muscle is the same length. In other words, it can't continue to overcome what that load was. If you go up to a wall and push against the wall, it doesn't mean that you're not engaging muscle in there and the sarcomeres are not trying to slide. They're sliding a little bit, but they're not pushing the wall down. Okay, so that's same length. Isotonic contraction changes muscle length, as I said, and it moves the load. So in these diagrams, these are the classic examples of physiologists that dissect out a frog leg, and then they use the frog leg. And this frog leg here is attached, and it's living still because they've just dissected it out, and it's alive, and those cells are still functioning, and it has a load on it. For the frog, 20 kilos is too much. It would be less than that. And if you stimulate it to contract, it's going to shorten and it's going to be able to lift the load. Okay, muscle contracts or muscle relaxes. If you were to chart it, you would see that the tension here developed is the same as the force required to move that load. So if this graph makes it up to the line here of that force required to move the load, you're going to be able to pick up the heavy bucket or pick up the table, your desk, or something like that. So always think of force overcoming the load, and the tension on that muscle is constant. You're able to hold it there. Okay, that's isotonic. Now there's different parts to an isotonic contraction. Those types of isotonic contraction are either concentric or eccentric. So concentric is what you usually think of as a contraction. Concentric contraction, the muscle shortens with the tension. That's what we've been talking about the whole time. However, there's a different form of contraction, and that's the lengthening of muscle. So you have tension on that muscle, but let's say it's the triceps opposing the biceps. There's tension on it, and it's balancing that opposing muscle. It's still considered a contraction, even though it's lengthening, but it's holding tension. And if it's holding tension, then we think of it as a contraction. So the example of lowering your weight against gravity. So if you had in your forearm, you had your elbow on a table, in your forearm, in your hand, you had a weight. And your arm is up, your hand is up, and you're bringing it down. You're bringing the hand down towards the table. And you don't want it to just slap down. You don't want it to crash. You're doing it slowly. Therefore, it's an eccentric contraction because it's stretching, but you're doing it in a controlled manner. We believe that when there is pain from excessive workouts, that most of that cell damage is done during eccentric contractions, the ones that are trying to hold that contraction without you slamming into the table, okay? Because you're holding it in place. It's deceleration, eccentric. I put this in because It's always sounded so funny for me when you think of someone like Donald Duck, right, with those big feet, and how they need that eccentric contraction for it not to slap down, not to flop. And it says, I'm going to read it, the tibialis anterior muscle in the shin flexes the foot up when it contracts. But when walking or running, it contracts eccentrically to control the descent of the toes after the heel strikes. Without it, your feet would slap something awful with every step. So it just sounds funny to me that we would flop around just because that eccentric contraction wasn't working well. Okay, how about back to the isometric, same distance. So in this case, you have a weight on the muscle of 30 kilos, and then this muscle contracts and it's creating force, but insufficient to lift the weight. So it stays the same length. This length hasn't changed. So it's isometric. If you would have plotted on the graph, then you would have this tension increasing, but then flattening out before it reaches the line which indicates the force required to move the load. So you can't really move the load. Contractions like this maintain posture also. They keep you upright. You're not moving anything specifically, you're just staying in that position where the tension is equal to the load. You're not trying to potentially move something away or lift, but just stay upright. So that's isometric. It's tricky to think about how tension is generated if the muscle doesn't shorten. It took me a while to think about this and think, well, if in the sarcomere, actin and myosin is sliding over each other, then it's going to shorten, and it's going to shorten a lot. And not moving, like pushing against a wall, not moving anything, sort of doesn't make any sense. But if we look at this diagram, it helps. If you had a muscle at rest, and these are the sarcomeres here, and they're overlapping very little. At the very end, you have to remember tighten. Remember that elastic element that's attached onto the end, essentially, of the sarcomere within a muscle. So in the isometric contraction, notice how in this part, the muscle actually is shortening. The muscle is shortening. But when you look at distance from here to here, it didn't shorten because it's the same as the distance from there to there. So somehow the muscle contracted, but it didn't shorten. So how did that happen? It happened because that elastic element was the one that stretched. And if that elastic element stretched, then it allowed for that shortening of those sarcomeres and no change in length. The isotonic contraction then, this line of course hits there, this line hits there. Oops, that's really hard to draw with the mouse, like that. And so there is definitely a shortening of that muscle. I hope that's clear. And that's the end of the shortest of these lectures, and it's the end of muscle. And I'm losing my voice because of the smoke. Take care. Bye.